Welcome everyone to the September ARC meeting. This is going to be another good meeting. Great speaker, and we've actually got some business to do. And we're going to do the business first, and we're going to get it out of the way quickly. We got two things to do. We got the election to do, and then we've got the repeater report from Jeff, and then we go into the main part, the fun part of the program. So without further ado, let me turn it over to N4BFR, the head of our election committee, Jim Reed.
All right, thanks, Rob. So at this point in time, I think everybody knows typically our elections are held in August, but due to some scheduling availabilities, we've postponed it to September. And we're going to conduct the election like we typically do in August, which means first we'll review the slates that have been submitted. We'll open it up to take any slates from the floor, conduct a vote, and then should be done fairly quickly. So there has been one slate submitted. There are 3 of the 5 people on the slate on this call. I'm going to ask Rob, do you want to introduce the slate?
I don't know who the complete slate.
Okay.
So go ahead.
The slate I have is John Talipski, N3ACK for president, Bill Perkins, KB4KFT for vice president.
Oh, wow.
Aid Shamblin, KJ4CUY as secretary treasurer, Rob Osattin, KI4UTY as member at large, and Ed Belleville, KO4SRJ as member at large. So since Rob, Aid, and Ed are here, do you all object? Are you all affirming your nominations? Because I haven't talked to you individually.
Yeah, yes, I'm good.
Ed's good. And Aid, I have talked to. So I'm assuming he would have said something when we went through all the slate vetting if he wasn't good with it. Okay, so that's our proposed slate of officers that we have right now. Are there any slates that would like to announce from the floor? Please speak up now.
Anyone?
Bueller.
Yeah.
Okay, I didn't introduce the other members of the election committee, by the way. I'm election committee chair. We've got Lane, KB4KHQ, and Newt, N4EWT are the other members of the election committee. So we've got a nice triumvirate to certify the election. Okay, since we only have one slate, let's do it this way. If there are any objections to the slate with John Talipski as president, please state them now. I'll go one more time. Any objections to the slate of John for the John leading being the 2022-2023 Atlanta Radio Club board of directors?
And please unmute before you say something.
Yes. Or write in chat. We'll do 5 more seconds and then we're calling it. Without objection, Aid, Newt, and Lane, do you agree that we have a slate properly elected?
I agree.
Yes, I agree, Jim. Thank you.
Lane agrees. All right, congratulations to John and the new board. The board officially takes effect at the end of this meeting. So congratulations, Aid, Rob, and Ed, and John, and Bill when they come along as well. So thanks to everybody for your help. And I turn it back over to Rob.
And thank you, Jim.
Thanks, Jim. Thanks, election committee. That was fast as promised. So good. We're good to go. Let me turn it over. Our next order of business is going to be a repeater report, and our repeater trustee has his church changed the schedule for his band practice, so to Thursdays. They wouldn't move it for us, so he's there, and Jeff is going to be making the repeater update. So please go ahead, Jeff.
Evidently the church doesn't know how important ham radio is.
They don't. Yeah,
All right, so pretty much reading this verbatim from what Stephen provided, but we did order a new RCOM RC210 controller, rack mount case, port expander board, real-time clock module, extended output board, and a partridge in a pear tree. Downloaded the RCP Windows programming software and started reprogramming the controller. He's saying we probably need an in-person repeater meeting at some point to determine where we go from here. I will echo point number 2. Both Stephen and I are very concerned about the situation at the bank tower, lack of an MOU. We really need to get an MOU in place with the new building management as soon as possible to ensure that we can remain up there, ideally free of charge.
Talk about an MOU. What an MOU is, please.
Memorandum of Understanding. So effectively I guess a legal agreement. I don't know if it's binding, but at least something that says, Atlanta Radio Club is able to occupy the space and operate repeater equipment at the top of the Bank of America building downtown. And, we won't go down there one day and find our stuff out on the street, which is a possibility as it stands right now, because there is no MOU in place. And I think we've gone through 2, maybe 3 management changes. Thankfully, the guy from, why is I drawing a blank on his name right now? Kevin from Altius has been great about advocating for the club, but Stephen and I both think that between GEMA, NWS, Track Club, ARRL, City of Atlanta, we can get enough folks to go to bat for us to justify our existence there. National Weather Service has already said that they will. I think Track Club would be pretty easy to get that one to happen too. Without us, let's see here, the link repeater net guys would have to link a lot more repeaters just to get the coverage in the metro Atlanta area, and even then there would be dead spots. Also, GEMA uses the Skywarn link repeater system, so it might be helpful to get buy-in from them. There are still some noise issues that we'll be looking into. Reaching out to Robert and Randy to get recommendations on filters that we may need, a filter or filters that we may need. Steven says he doesn't think that there's any way to have 2 UHF repeaters going simultaneously at the bank tower with the 2 separate antennas that we have, even if both of them are good. They're both on the same level at the tower, so there would be no end of descents problems if we want the 440 analog repeater back on the air. Best bet would be to purchase a UHF combiner from Bridgecom or someone else that will allow us to split out UHF antenna that's being used for a DMR repeater with an analog 440 repeater. Yeah, sure, we understand that there may be some loss or 3 dB loss with the combiner, but can be mitigated with the preamp on the receive side and power amplifiers on transmit side. We'd need a UHF duplexer for the analog repeater. I think we have one somewhere in our inventory. It's just money. Who cares? Whether it works or not is a different story, is what he says, though. Yes, sir.
A question on 440 analog. I thought that part of the reason why we converted, when we converted to DMR, there were no 440 pairs available in the metro area. Has that changed?
Do not know.
Okay.
Yeah, we have not approached Sarah yet about that. I did talk with Sarah last year and said that I was interested in a UHF pair, and the answer I got was, as long as you're not interested in a VHF pair, they should be able to do something. So, I mean, it sounds like VHF is pretty much next to impossible, but I think we can get a coordinated pair for UHF.
It's narrow bandwidth too, so that makes it a little easier, right?
Well, yeah, so, I mean, for analog, we would be getting a new pair for analog, right? So that would be 25K. It would not be narrowband.
We'd have two wide bands. Okay.
Yeah, we would have to, we kept the wideband pair, so in theory, or at least based on Sarah policy, we probably should have changed the pair when we switched over to DMR. But because it is a dual mode repeater, analog and digital, they decided to let us continue using the pair as is. In the event that we ever needed to switch it to analog mode, we would be ready to go.
No, that makes sense. Yeah.
So,
Are all the repeaters working?
yeah, as far as I know, yes.
Okay, that's good to know. I mean, that's
Yes, the DMR repeater is rock solid as always, and the Vertex seems to be doing a decent job. The Majori, I don't really get on 220, so I can't say.
and D-Star's up.
D-Star is rocking and rolling.
Good. That's our repeaters. Yeah, both Bank Tower and Stone Mountain. Right. That's our collection.
Oh yeah, not sure what's going on with Stone Mountain for D-Star. I think those may be collecting dust, but not really sure. We need to get with somebody who has access to the portion of the building where those repeaters are. I was just there a few weeks ago helping out the Alfred Memorial group with their DMR repeater, but they are in a different room than where the D-Star equipment is, so I was not able to get access to them.
You know, that'd be a good thing for the repeater committee to talk about. Thanks, Jeff. Thanks. Anybody have any questions? I know everybody wants to get to the main program. Everybody wants to hear what the heck is a Smith chart. We've heard the name. We've seen we've seen graph paper with all kinds of circles on there, and so I'm ready to hear about it. Or we have a expert speaker tonight, Alan. I'm gonna go ahead with Alan Wolke. Did I get that right, Alan?
Yep, you got it right.
Yeah. W2AEW, and I'm being that I'm a Yankee, I would say, yeah, he's from the north, so he's smart. I know. I'm going to pay for that. But anyway, let me turn it over to you. Appreciate your waiting with us here. So over to you.
All righty, very good. Appreciate that. Thank you very much for having me. Thank you for the invitation. You'll have to give me permission to share. So while you're doing that, I'll just a quick introduction to myself. W2AEW, born and raised and still in New Jersey. Don't hold that against me, especially with the accent. So, so I've been a life member of the ARRL, been a ham since probably 79 or 80. So a little over 40 years. And current profession is a field application engineer for a little company called Tektronix, who most of you are probably familiar with. So, so I spend my days playing with the latest and greatest stuff, and then my evenings playing with the old stuff in my basement. So, but all right, with that, let's see. Let me go and bring up a share here and start with our presentation. So let me. I'm going to share this with sound because I do have an embedded video on one of the slides here. So, all right, someone give me a thumbs up that we can see all that.
Looks good.
All right, beautiful. Okay. So yeah, so let's just jump right into this. Let's see. All right, so our agenda tonight. First, obviously, what is a Smith chart? We'll talk about what that is, some of the regions on a Smith chart and that type of a thing. But we'll talk a bit about antenna measurements and transmission line effects and how they're represented on a Smith chart. And then take a short little look at a video showing how you can actually use something like a NanoVNA and the Smith chart to watch your manual tuner in operation. Let's actually see what it's doing. It's kind of interesting. And then a little bit of a bonus at the end, we'll talk about how you actually design an L matching network using a Smith chart. And of course, there's automated tools and simulators and things like that nowadays that we can use. But it's kind of interesting to kind of see how that was done graphically years ago before we had these tools available. So let's start off with what is a Smith chart. It's really kind of a graphical tool to both plot and compute various things, including complex impedance. That's kind of the fundamental thing we're computing with that. And then also look at the complex reflection coefficient, right? The complex reflection coefficient arises from having a complex impedance at the end of a transmission line that doesn't match the transmission line impedance. So the reflection coefficient will have a magnitude and phase. So we'll be able to look at that as well. The thing that we're going to talk about probably the most interesting to us as hams is the SWR or VSWR. We'll chat about that and how that's represented on a Smith chart. And then we're also going to talk a bit about transmission line effects, because interestingly enough, the Smith chart was developed as a transmission line calculator aid to aid with the often very complex computations that are involved in predicting what goes on in the transmission line. The equations involve things like hyperbolic tangents and all kinds of ugly math, and the Smith chart kind of alleviates you from doing all of that. And then we'll also talk a bit about designing matching networks with the Smith chart. Of course, there's a whole lot more you can do with a Smith chart, but we're not going to talk too much about that. But this will kind of cover the things that'll give you the basics of what the Smith chart's all about. So let's break this down. I see the chat came up here. I'm not going to keep an eye on the chat. So if someone else does, and there's a question that comes up in it, just let me know and we'll pick it up that way. So. All right, so the first thing we want to talk about just as a concept is something called normalized impedance, right? A Smith chart isn't really designed for any particular system impedance. It could be used for 50 ohm system impedances like most of us are going to use, but also could be for 600 ohm lines, could be for 93 ohm lines or 75 ohm lines. So in order to use the chart in any system impedance, the chart is kind of printed in and used in what's called normalized impedance, where we take the actual impedances that are measured and divide them by the system impedance. In our case, and what we're going to talk about today, let's just assume that the system impedance Z0 is 50 ohms. All right. So in our case, for a 50 ohm system impedance, all we're going to do is take our complex impedance values and divide them by 50 to get a normalized impedance. An example, let's say I had my fancy antenna analyzer that reported a complex impedance of 37 ohms plus an inductive 55 ohms of inductive reactance. To normalize that, we simply divide each term by 50, and we're left with a normalized impedance, which is indicated by the little prime symbol here, of 0.74 plus J1.1, okay? Now, this makes the chart usable really for any system impedance. And more importantly, this is what we plot on the Smith chart, is this normalized impedance, because all the numbers on the Smith chart are really geared around this normalized number, okay? So that's just one concept to kind of get out of the way before we get started. So let's take a look at some of the regions of the Smith chart, how we break it up and where things are represented. I mean, it looks like a pretty complex thing, but let's kind of break it down here. Because in a sense, the Smith chart is nothing more than graph paper. It's graph paper that is just kind of curled around on itself, as opposed to rectilinear like we're normally used to with graph paper. But in a sense, it's just a fancy graph paper with curved lines instead of straight lines. Right along the center, we'll call it the prime axis, or right through the the equator, if you will, of the Smith chart, is represents impedances that are purely resistive, meaning that the reactive component is 0. So the X in JX is 0. So basically anything that lies on this line in the middle is a pure resistance. Any dot or point or trace that lies above in the upper hemisphere here is a complex impedance where the reactive component is inductive, meaning I got a positive J, okay, in terms of the reactive or the complex impedance. And obviously, as you'd expect, then the lower hemisphere is for the negative J or capacitive reactance. So if you've got a complex impedance where the reactive component is capacitive, that's going to lie down here on the lower half of the Smith chart. So let's look at some key values on the Smith chart here. First one, right here, dead center, right? that represents our system impedance. Okay, so if we're talking about 50 ohms, that's where 50 ohm lies on the Smith chart, right there, dead center. That's where we want to be. Okay. Over in the 3 o'clock position over here, that represents an open circuit. Okay, effectively infinity. Okay, right there on the edge, right at 3 o'clock. That's where an open circuit or very, very high impedance is represented on the Smith chart. And then conversely, over here at the 9 o'clock position, that point right along the perimeter represents a short circuit, 0 ohms right there. So you might look at this and say, well, gee, I go from 0 ohms to 50 ohms in the center, but then I go from 50 ohms to infinity over here. So what you can kind of infer from that is that the Smith chart really isn't going to be usable for looking at impedances that are very high. Once you get above several hundred ohms or a few K ohms, a Smith chart really isn't usable anymore. It isn't going to give you very accurate results. So it's really when you're, ranging from 0 ohms up to a couple of hundred ohms, that is probably the best usable area for a Smith chart. Okay, which is fine because most of the time, in our case, when if the system impedance is 50 ohms, right? If the system impedance was 600 ohms, then we can go a bit higher. But you probably say 10 times the system impedance is about the highest impedance you can kind of realistically think about looking at on a Smith chart. So let's break down what these curves are. So if you look at this, there's actually a series of circles right here and here, and the one I've got highlighted in blue here, and then around it, all of them being tangent to my open circuit position here. Okay, and those represent essentially a constant resistance, a resistance of 1. Okay, so that's your resistance of 1 circle there. Okay. So that's what's represented by these circles. And then as you move around, each of these other circles represent different resistances. So in our case, this R prime of 1 means that's our 50 ohms. Okay. So in this case, here's the R prime of 3. So that would be 150 ohms. So if you looked at the complex impedance, R plus JX, the R part of it, if something lies on this line, would be 150 ohms. Here's the R prime of 0.4, so that would be 20 ohms, right? So anything lying on that line would have a 20 ohm real component to the complex impedance. All right, so that takes care of all of these circles that you see. Okay. Is there a question? Okay. All right, so if we zoom in on the center portion of this, we can kind of see those numbers here, right? So right here, you can kind of see it's a little fuzzy, sorry about that. 1.0, right? That's the R 1.0. So that's our 50 ohm point, right? That's this point right here. We can see 0.4 here, 0.5, 0.6, then going higher than 1, 2.0, there's 3.0. So that's your 150 ohms. Here's 4.0, that would be 200 ohms, right? 250 ohms, etc. Okay, so that's how you read that. So that's where you get the values for each of those circles. Now, the arcs that we see are also part of circles, but we're only seeing the portion that lies within the circle here, right? But these arcs are essentially our constant reactance arcs. All right, so I've got highlighted here the normalized inductive reactance of 1.0, okay, or in this case, 50 ohms of inductive reactance. And then this is the 50 ohm capacitive reactance arc. All right. So, and then here's the J plus 0.5 and J minus 0.5. So this would be plus and minus 25 ohms of inductive or capacitive reactance. So as these arcs get closer and closer to the prime axis, this number is getting smaller till you get to the point where, again, where the X reactive component is 0 and you're lying right on this line. Another point I should make is that if you're lying right on this line where you have no reactive component, what's another name for that? Another name for that is resonance. The strict definition of resonance is that you have no reactive component in your impedance. It's pure resistance. Resonance doesn't mean 50 ohms. Resonance just means that your impedance is just resistive. There's no reactive component to it. All right, so anything that's lying on that line is technically a resonant point. Right, so how do we plot a complex impedance on the Smith chart? we start off, let's say, okay, here's the complex impedance I got from my antenna analyzer or my simulator or computations of the circuit I'm building or whatever. 25 ohms plus an inductive 40 ohms of inductive reactance. The first thing we want to do is divide by 50 to normalize it. So that leaves us with a normalized impedance of 0.5 plus j0.8. Okay. So all we have to do is find the intersection of the 0.5 resistance circle and the 0.8 arc. So here's my 0.5 resistance circle. I can move, kind of go up on that. And then here's my 0.8, positive 0.8 inductive reactance arc. We follow that down, and right there, there's where that complex impedance is plotted on the Smith chart. It's right there. It's as simple as that. So any point on the Smith chart is just determined by, and can be read by looking at where that point is and looking to see what arc it's on and what circle it's on. So let's take a look at how this relates to frequency, for example, because nothing on that Smith chart that I showed you had anything to do with frequency. And that's the only unfortunate thing with the Smith chart is that you don't have any indication of what frequency is going on. So tools like a NanoVNA or something like that, you've got to figure out frequency some other way. Okay. So let's take a look at antenna impedance versus frequency. And here's a plot from a NanoVNA here. Okay. And there's two traces on here. This green trace that I'm kind of tracing around here is the complex impedance over a frequency range. We can see here from 13.7 megahertz up to 14.7 megahertz. So this is over a little bit wider than the 20 meter band. Okay. This is just sweeping one of my antennas. All right. So the complex impedance versus frequency is shown in green. And again, you don't get frequency on this axis at all. So I've got a marker on here. This marker number 1 is sitting at 14.245 megahertz. So that's the only way to figure out where you are in frequency on a curve on a Smith chart, is usually using some kind of a marker. Now also plotted on here in the white trace, this is one down here going like this. This white trace is an SWR plot. So the SWR plot is using the rectilinear, axes, where the Smith chart is using the curved axes. Okay. So we can see, for example, that the SWR reaches a minimum. I've got the marker sitting kind of at the minimum of that. So again, at 14.245 is where my antenna's got the lowest SWR. Okay. At the low end frequency, we can see this SWR came up to about 6.5 to 1. And that's also corresponding to this point on the Smith chart here. Okay. And at the other end, at 14.7 megahertz, we're about what, 2, 3, 4, about 4.4 to 1. And that would represent this point over here on the Smith chart. And of course, if we move the marker around, you'd see all of that. Now, one thing you'll notice from this, if you look carefully, is that these markers are sitting at the same frequency, so that the minimum SWR occurs at the point on this curve that is closest to the center, right? Remember what we said, the center is 50 ohms. So the point on this curve that is physically closest to the center is where the minimum SWR is. So that kind of gives you a hint of how we look at SWR on a Smith chart, right? How far away are we from dead center of the Smith chart tells you what the SWR is. Okay, so we can tell I've got the worse SWR here and here than I do right there. And we can also see that this point at the lowest frequency is further away from the center. So that's going to give me a higher SWR than that point over here. Okay. So again, the markers on like the NanoVNA and other tools will generally be linked in frequency. So you can kind of pick things out at the same frequency at different spots on the curve. We're going to return to this plot and some things in a slide or two. But let's kind of expand on this a little bit. So a little bit of how do we actually read some of this stuff? So on a real Smith chart, actual paper one, there are actually what we call radially scaled parameters, and they appear down along the bottom of the Smith chart itself. And this is how we would read things like SWR. Okay, there are a number of different radially scaled parameters, both here and there's some over on the other side that I'm not even showing that we're not going to talk about. We're just going to talk about a couple of them here. So the way you use that remember we said that the SWR is proportional to the radial distance from the center. So the way we do that is we take and we rotate, we can do this with a compass if we're going to do it graphically or visually kind of do it. Rotate this point around, equidistant from the center, from the center point here, till we hit the prime axis. And then we drop a vertical line down. And then where it crosses all these scales, we can read off various values. We can see this first line here says SWR, right? So if we drop down straight from the center, we'd be right here at 1:1. But where we drop down here, we're right at 2.3:1, right? There's 2, there's 3. So that's a 2.3:1 SWR, that impedance right there. That's how you measure it, okay? Also shown here, we have return loss, 8.1 dB, and reflection coefficient for power and voltage and current. They're all shown on these radially scaled things. So real quickly, we can relate SWR and return loss and things like that to a given impedance. Now, what's interesting with this, if we extend this a little bit further and trace a line all the way around, okay, we traced a line up to this point to kind of read that radial parameter because we said that's how we get to an SWR. But what's the implication there? The implication is that any point on this curve that I've just drawn that bisects my point here and centered on the center, any point on that curve is going to have the same SWR. So that's interesting, okay? So what that means is there's really an infinite combination of complex impedances that will result in the same measured SWR. Okay, and we can call this a constant SWR circle, all right? Now, what's really interesting about this is that when we add feed line between our antenna and our transmitter, that's the same on a Smith chart as rotating clockwise around this circle, all right? Because adding or subtracting feed line does not change the SWR. It does change the complex impedance, but it doesn't change the SWR. So adding feed line effectively just rotates us around the Smith chart in a clockwise fashion on this constant SWR circle. Subtracting or removing feed line rotates us counterclockwise around that circle. And you might say, well, I don't know. I don't know that, if I believe that changing the feed line length doesn't change the SWR. Well, there's two things to kind of consider. One is if the antenna feed line itself is actually a part of the antenna, meaning that it changes the antenna's feed point because of the feed line being there. Maybe the feed line is part of the radiating element or is part of the counterpoise system. Then indeed, you may not follow this constant SWR because you truly are changing the antenna's impedance by changing feed line length. But if the antenna, or excuse me, if the feed line is not really part of the antenna, then you'll follow around this constant circle. Now, also, this is assuming that the feed line is lossless, right? So if a perfect lossless line, we kept adding line, we just keep going around and around and around. But in reality, there is some loss in feed line. So that means as you add feed line, this actually starts to spiral inwards. And if that line were infinitely long and lossy, it would look like 50 ohms, right? So, but the other argument might be, well, I've got an antenna tuner that doesn't like tuning on 80 meters, but if I add 5 feet of coax, it does tune on 80 meters. So that means the SWR must be changing when I change the line. Well, that's not necessarily true. What that means is that your antenna tuner might have an easier job tuning this complex impedance versus that complex impedance due to the reactive, the inductors and capacitors that are inside the tuner. It may not have sufficient range to compensate or tune for this impedance, but it can for that one. So it's not really just the SWR that you got to consider in terms of how the tuner is going to perform. It really is what is the complex impedance and what is it made up of? Where am I on that circle, right? Which may determine how well a tuner works, for example. Okay. So now what's also interesting is that one trip around the Smith chart, like if I go from here, add some feed line until I get right back here, that's a half wavelength of transmission line length. All right. So if I do it again, that's another half wavelength. So what the implication there is kind of interesting, is that if the feed line between my transmitter and my antenna happens to be a multiple of half wavelength, that means that the actual impedance seen by my transmitter is equal to the impedance at the feed point of the antenna. If it's not a half wavelength, the feed point impedance at the coax input at the transmitter end is not necessarily going to be the same as the actual impedance at the feed point, although the SWR will be the same. Okay. So again, with the half wavelength, the impedance repeats. Now halfway around the Smith chart represents a quarter wavelength transmission line going from here to here. So what are the interesting things there? Let's say I had a quarter wavelength line that was open at one end. If you took a quarter wavelength line, left it open at one end, at the frequency where it's a quarter wavelength long, it's going to look like a dead short at that frequency. Okay. Similarly, if I had a shorted piece of quarter wavelength line, okay, it will look like an open circuit at that frequency at which the feed line length is a quarter wavelength long. So one interesting thing is, let's say you took your piece of coax and you put a little T in the middle of it, and you attached another piece of coax to the end of the T and left the other end of it open. If you tuned up to a frequency where that open stub of feed line was a quarter wavelength long, it's going to look like a short circuit at that frequency. At other frequencies, it won't look like that. So it's like a really sharp notch filter that's just nothing more than an open piece of coax. Okay. Now, so it's also important to remember that this characteristic repeats if I go a quarter wavelength or 3/4 of a wavelength. So at odd quarter wavelength multiples of feed line length, the same behavior repeats, just like on that when you go half wavelength, halfway around, you repeat the impedance, halfway around again, you repeat the impedance again. So each time you go, so you're really kind of alternating between inverting the impedance to matching the impedance, to inverting the impedance to replicating the impedance. So for the quarter wavelength line, kind of the general rule is an equation like this that says that if I have a given impedance here's my system impedance. So I've got a given impedance and I move a quarter wavelength line away, this relationship holds true. Okay, basically invert this. Z0 goes to the top and you get a new impedance down here. So you can compute the difference. Now, obviously, if we had a short circuit, for example, if Z1 was 0, then I have a divide by 0 here, which means infinity, right? Open circuit, and vice versa. So that's how that works. So you can see there's some interesting things that happen by adding and removing transmission line length. So let's take a practical look at that, of adding coax length. So here, I'm going to show you some results of the same exact antenna measured on a Smith chart and with an SWR, and just changing the transmission line length. So here's our starting point. Okay, this is the same chart I showed you earlier. There's my complex impedance. There's my SWR curve. All right. So now let's add about 3 feet of coax. All right. So now what you can think of is that any point on this curve is going to rotate around its own concentric circle around the center. So you can kind of see this whole curve effectively rotates itself around the center. All right, just by adding 3 feet of coax. You'll also notice the SWR curve hasn't changed. My minimum is still at the same point because the point that I get closest to the center is still at the same point. Okay. Add another 3 feet of coax. I rotated clockwise a little bit further, with this same C-shaped curve. SWR is still the same. And then a final 3 feet of coax, I've rotated around even more. So by adding, say, 9 feet of coax, I've taken this complex impedance trajectory and changed it to this. Okay, but the whole time, my SWR curve over that same frequency range has remained the same. Right. So again, no change in SWR, just a change in the complex impedance that's being represented at that input of that coax. Okay, but you're not changing the SWR. So let's talk a little bit more about transmission lines and how we can actually use this to do some things for us. We can actually use this to predict what the impedance is for a given line length. Let's say, for example, I know that I measured my impedance here at the transmit end of my coax. All right. We can take a look at along the outer perimeter of the Smith chart. If we magnify that a little bit, we can actually see these words here that these scales on the outside are calibrated in wavelengths toward the generator or transmitter, and then going this direction, wavelengths towards the load or the antenna. So we can kind of see that. And again, if you look at this, like this chart here, there's 0.47, 0.48, 0.49, then it goes to 0, and then starts counting up. So again, that's our halfway around, or 0.5 wavelengths around, and we go in opposite directions. So let's say, for example, I measure a complex impedance here at the transmit end, and then I can rotate. If I know my line length in terms of wavelengths, I can then rotate along this constant SWR circle that number of wavelengths. And now I know what the impedance is at the feed point of the antenna, okay, by measuring it at the other end. Now that might be important because the antenna might be far away. You're not going to get up, climb the tower to get to it very often. But if you want to design a matching network, ideally you want that matching network to be at the antenna end and not at the transmit end. Now you know the impedance that's at the transmit end. So you can then design and build your matching network. And the next time you climb your tower, throw it up there, and then you'll create a nice low SWR point, for your operating frequency without having to go up and measure it right at the antenna. So let's talk a little bit about resonance and minimum SWR. Dispel a couple of myths here as well. Again, remember I said earlier, resonance only means that the reactance is 0. So here I've kind of zoomed in on a portion of that graph I showed earlier. In fact, right where I've got my little laser pointer, that's actually the center of the Smith chart right there. So sorry I didn't center it up on my crop here, but that's the center of the Smith chart, right? So, and my marker is still sitting at the minimum SWR point. Okay, but if we look at this, this is where reactance is equal to 0, right? Along this line here, that's actually the center of my Smith chart. So how many resonant frequencies are here? So if we look at it, well, there's one right there, right? Remember I said any point that lies along this axis is a resonant point. So there's a resonant point right there, but there's another one right here, right? Across that center axis there again. So this particular antenna system, meaning antenna plus feed line, actually has 2 resonant points. But what's the other important thing here? Neither of those is where the minimum SWR occurs, right? The minimum SWR occurs on the point of the curve that's closest to the center, not necessarily the resonant point. Now, we always get in the habit of saying, I'm going to tune my antenna to resonance. And really what you're doing is tuning to minimum SWR. That may or may not be the resonant point. You might still have some reactance there, okay? Doesn't matter, okay? You're still likely going to be most efficient by operating at the minimum SWR point. Now, of course, the reality is the reactance is going to be relatively low. If you're close to the center, it means you're close to the center vertically as well as horizontally, right? So it's still going to be a low amount of reactance, but this complex impedance here is going to give you a better match to the transmission line than that resonant point and that resonant point. Okay. So again, we always get in the habit of adjusting my antenna to resonance. The reality is you're really adjusting your antenna to minimum return loss, minimum SWR, not necessarily to resonance, because resonance and minimum SWR don't always occur, and oftentimes don't occur at the same frequency. So a little brief thing is, how do I set up a NanoVNA to measure an antenna or an antenna system? Okay, maybe measuring it, at where my transmitter would connect here, right? So what you do is you select what traces you want to have open. Remember, the NanoVNA has 2 ports. Unfortunately, they call them channel 0 and channel 1. But channel 0 in VNA parlance is really called port 1, in reality, but the NanoVNA folks for some reason called it channel 0. So channel 0 is the port that can source an RF signal and then measure the reflecting signal coming back. So that's our channel 0. So what I will typically do is set up 3 traces. I'll set up the SWR trace, I'll set up the Smith chart, and I'll set up what's called the log mag. Log mag is the log magnitude of the reflection coefficient, or the S11 trace. All right, so we'll set all those up. So in this case, we look, the yellow trace is the log mag, that's this guy right here. All right, the green is a Smith chart, that's this one right here, the Smith curve. And then the kind of blue trace here is the SWR, the white one here, that's the SWR chart. Okay, and they all can be plotted, at the same time. All right, all of those use channel 0. So those are the traces that you would enable and set up on the NanoVNA. Then you set up your stimulus range. What frequency range do you want to measure over? Start frequency and stop frequency. You don't want to go too wide. If you got a multiband antenna, you might be tempted to measure over a very wide range. The downside to doing that is that there's a limited number of measurement points that the NanoVNA uses. The early firmware was like 101 points. So if you measured from 1.45 megahertz up to 30 megahertz, you're not going to get a whole lot of points landing in each amateur radio band. You won't have a lot. You won't have a very good granularity between the points. So it's a good idea to make your frequency range, kind of focused where you're interested, to concentrate those 100 points or 200 points or whatever you got in your trace across the frequency range of inches, so you've got good resolution in the frequency measurement points. And then you want to calibrate it. NanoVNA, because it can measure phase and because it has a very wide measurement dynamic range, does benefit from a local user calibration once you've set up the frequency range. I've got a whole video on that. We won't get into the details of that right here, other than showing you in the video how to do it. Okay, so once you've set up your traces, set up your stimulus range, run your calibration, and then go ahead and make your measurement, okay, which is what we've done here. So at this point, I've got a short video, about 6 minutes. This is most of video number 314. That's going to walk through that setup, calibration, and use, and then also show you how the NanoVNA can be used to visually see what's going on with your tuner. So let's see if we can get this going.
We can see that the yellow trace is already set up to be the log mag of the reflection coefficient, so we'll leave that. The green trace is already a Smith chart, so we'll leave that one alone. So we'll reconfigure the blue trace to be SWR and then get rid of the purple trace. So we bring up the menu, go to display, go to trace, and let's first just get rid of purple trace by touching on it again to get rid of it. And then we'll select trace number 1. The inverse text tells us we're selected. We'll go back and then tell it to be on channel 0, which is the reflection channel, or the S11 channel. And now we just have to go back in one more time to the format and hit SWR. Next, let's set up the frequency range we want to test. So we'll bring our menu back up and go back and back again and go to stimulus. In our case, I want to measure the 40-meter amateur radio band from 7 megahertz to 7.3. So I touch on the start frequency, and I dial in 7 M for megahertz. That will set up the start frequency, and then we'll go back in and select the stop frequency, 7.3 megahertz. And now we've set up the stimulus range that we want to test. The next thing we want to do is run the calibration. So we go bring the menu back up, go back and hit Cal, and go to reset the existing calibration. We can see that those calibration indicators have gone away over here. And then we hit calibrate. And since we're only doing a reflection measurement on channel 0, we only have to do an open, short, and load. So we start off by putting the open on the port and touching open. And next we put a short on the port and touch short. And then we replace the short with a 50 ohm load on the port and touch load. Once we've done all 3 standards, we can hit done and then choose to save it to a memory location. I'm going to choose just to save it to location 1. And so now we hook up the antenna With the antenna hooked up, we can see our SWR plot over the 40-meter band. We can see the log magnitude of the reflection coefficient, and we can see the Smith chart. And we can use the jog wheel to move our cursor or marker to make measurements at various frequencies across the range. Or we even have some marker functions to search for a min or a max. So for example, if I touch on marker number 1, that activates trace number 1, and I can go into the marker function and do a search and search for a minimum, and that will put the marker right at the minimum. And I can see that's at 7.216 megahertz. Now of course that's all we need to do if all we want to do is to sweep the antenna. But if we want to retune it, for example, we can leave these displays up and actually watch the reaction as we adjust the tuning on the antenna. So let's say, for example, I want to retune to be closer to the middle of the CW portion of the band instead of in the phone portion where it is now. So we can actually just watch the reaction on the VNA as I tune the controls on my antenna tuner. And this is where I find it handy to have the Smith chart shown on the VNA, because you can actually see how the controls on the antenna tuner are going to twist and roll the trace on the Smith chart, and it gives you a little bit better intuitive feel about which way to tune the various controls. Now the first thing I'm going to do is move my marker down to somewhere in the CW portion of the band, maybe around 7.07, 7.06, 7.05, something in the neighborhood. So to give me an idea, that's the point that I want to now try to optimize with the tuner. All right, we'll start by moving some of the dials around here. Let's take a look at how the various curves move around. We can see as I turn my inductor up, I can see the Smith chart's kind of turning around in this direction. And we can actually see I'm bringing my marker on the Smith chart closer and closer to the center of the Smith chart. So I'm getting kind of close, but it's still kind of missing the mark a little bit, so we're probably going to have to optimize the capacitor here as well. So if we tweak on that a little bit, I can see I'm deepening the null there on the reflection coefficient, and I'm getting pretty close. So you can see with just a little more fine tuning on the controls of the tuner, I've got myself pretty darn good at my desired point right there. SWR is about 1.02. I'm sitting right at the center of the Smith chart.
So that's just a quick example of how you can use, if you've got a manual tuner, you want to do some playing around with the NanoVNA, you can actually see what you're actually doing when you're adjusting the tuning network. So in a sense, the tuner I was using was actually an L network tuner. So kind of the little bonus part here is how to design an L network using the Smith chart as a graphical computing tool. Okay, so we're going to kind of go through the process that we were visually seeing happening by adjusting the inductor and capacitor in my L network tuner. So an L network is really just adding a series or parallel inductor or capacitor to move from our measured load impedance to right to the center of our Smith chart. So the L network topology that you can use depends on what load impedance you're starting from. And we've got these kind of yin-yang diagrams that kind of show you that. These four over here are probably the most common, because these we use with both an inductor and a capacitor. There is possibility for certain impedances to use purely capacitive or purely inductive matching networks, but they won't match every possible impedance. So what this is this just a overall view of the Smith chart, and this shows you the region of capacitances, or excuse me, the region of complex impedances that this network can tune for. This shows you this is the region of capacitance or complex impedances that this network can tune for, and so on. And you'll often find that that sometimes usually at least two of these topologies will work. So which one do you use? Usually you make that decision based on maybe the available components you have, okay, in terms of which is going to give you components that are closer to things that you've got in your junk box or that are in your tuner itself, or whether you want the tuning network to be a high pass or a low pass network. So for example, if I have, say, an impedance right about in this area here, I could use this network or I could use this network, right? So I can use a series L and shunt C, or a series C and shunt L. This guy is a low pass network. This is a high pass network. The advantage of the low pass network is that it's going to give you some harmonic rejection. So maybe that's the better one to use. Okay. But you can kind of, again, your decision process of which one to use might, depend on, the whether it's a high pass or low pass network, or what components you've got available. All right. So when we add elements in series, what does that do on the Smith chart? Okay, we're basically moving our impedance around. Adding elements in series are going to move us up and down on the constant resistance circles. Okay, so in this case, I'm lying on this, 0.5 constant resistance circle. So if I add a series inductor, I'm going to move in this direction on that constant resistance circle. If I add a series capacitor, and if I do that, I just read the values here. I went from 0.8 to 1.4. So I've added a normalized capacitive reactance of 0.6 by going from here to here, right? Similarly, by adding a series capacitor, I move my way down that way. And again, we can use the numbers again to figure out what my normalized capacitive reactance that I added was, okay? So now what about admittance, right? If we're adding series components, we can just add them up, right? Z1 plus Z2 plus Z3 equals Z total, right? It's easy. But when you add things in parallel, then everything inverts, right? 1 over Z1 plus 1 over Z2 plus 1 over Z3 equals 1 over Z total. So it's a lot harder to deal with. But if you invert everything and talk about things in admittance, then you essentially can just add things up, right? So when adding parallel components, it's handy to talk about admittance. And again, admittance is just 1 over impedance, right? And individually, like 1 over resistance is conductance, 1 over reactance is susceptance, right? But when you have a complex value that includes both Z and X, right? R and X, then you can't just invert each term. It becomes more complex than that. But the Smith chart actually makes it very easy. So converting an impedance or complex impedance to a complex admittance is simple on a Smith chart. So here's how you do it. So let's say I have this complex impedance here, but now I need to add a component in parallel. So it'd be handy to convert this number to its admittance, complement. So we draw our friendly constant SWR circle. We bisect that circle from our measured point down to here. And this point down here becomes our complex admittance. Simple. It did all the complex math for us. So we went from, in this case, a normalized complex impedance of 1 plus J 1.1, and the complex admittance of that is 0.45 minus J 0.5. And it was just done graphically. So very handy. It's a lot easier even than punching it in a calculator. Okay. So, but if you think about it, well, all we did is we rotated 180 degrees. So if we took a normal Smith chart and we rotated 180 degrees, that chart is an admittance chart, right? So I've got a complex impedance chart and a complex admittance chart just by simply rotating the whole chart by 180 degrees. That's all we did by going halfway around that SWR circle. Now, if you take a look carefully, you may not have noticed it before, but the chart that I've been using all the time has got all these red lines that we've been paying all of our attention to. They're all of the complex impedance curves for resistance and reactance. But the blue curves on here, you can see now there's blue curves going the other way. Those are the impedance curves. So the circles of constant conductance and arcs of constant susceptance, right? So just like that. So this chart actually has got both pieces on it. So this actually makes it handy when it comes to designing a matching network, right? So if we add elements in parallel, so we're doing the same thing that we did when we added elements in series, but now we use the blue curves, all right? So adding a shunt inductor or capacitor moves along the constant conductance circles. So adding a parallel inductor, adding a parallel capacitor, just like that, all right? So, and then again, we read now the blue numbers to figure out how far we went, okay? So by doing this, we can kind of zigzag our way around the chart to create a matching network. All right. So now how do we figure out what direction we go in when we add components? Because you can go one way or the other. So I've got a couple of goofy, corny ways of remembering that. When we're talking about inductors, when we're adding inductors, we elevate through the real axis. So what I mean by that, if I'm adding a series inductor, I'm going up through the real axis, the prime axis, elevating through it when I'm adding more and more inductance. And if I'm adding parallel inductance, I'm going up through on the constant conductance circles, right? And then equally corny capacitors, I kind of crash down through the real axis. I go the opposite direction. So that's how I remember which direction to go if I'm going to be adding inductors or capacitors in parallel or in series. All right, so remember this when we design a matching network. So here's the design process. I typically would start by highlighting the R and G equal to 1 circles, because that's our target. We want to get onto that so we can finally rotate down to the center. All right, so we pick a topology based on where the impedance is. So where this impedance is, I'm going to pick this topology, which is a series inductor and a shunt capacitor. So we start here and we're going to add a series inductor that rotates us up the constant resistance circle until I hit the unity circle here. Now I know I can, by reading how far I added here, I know how much inductance I've added. And then I'm going to add a shunt capacitor, which is going to go down along the constant conductance circles, or actually in this case, go right down this one here, adding that shunt C. And again, looking at how far I went, I compute those values to figure out what I have. So we'll do a quick example to show you what we're talking about. All right, so step one. Here's my operating frequency, 432.1 megahertz. With my analyzer, I measured 75 ohms with 60 ohms of capacitive reactance. So we normalize that, plot it on the chart. That's step number one. But now we need to move this point to here, right to the center. All right, so based on where this is, I'll pick a topology. I'm going to use this topology here, which starts from the load by adding a shunt inductor. So that's our first task. So I'm going to add a shunt inductor. I'm starting here. I'm going to highlight my, R prime equal 1 circle. I'm adding an inductor, which is I'm going to go up in this direction. I'm adding it in parallel, so I'm going up on the blue circles up to here until I hit that circle, the circle right here. Now I take a look at how far did I go. I went from this point here, which was at about 0.32 or so. Okay, that went up to 0, and then another up following this blue curve, that's 0.5. So 0.32 plus 0.5. I moved a normalized capacitive susceptance of 0.82. We invert that to get the normalized capacitive reactance, multiplied by 50 to get to the actual capacitive reactance of 61 ohms, and then compute the inductance value since I know my operating frequency. So 22.5 nanohenries is the shunt inductor we're going to use to move us from here to here. Now we go and add the series capacitor here to rotate us down this far. So we rotate down, we take a look at that was moving a minus J 1.2. Okay, we multiply that by 50, again, 60 ohms of capacitive reactance. We can compute the capacitor value, 6.14 picofarads. So now my matching network to take this complex impedance and make it look like a 50 ohm resistive input is a 6.4 picofarad capacitor in series with a 22.5 nanohenry inductor in parallel with my load. So that's how we did that. Okay. Now, of course, there's tools online to do this. There's programs that can do all this for you automatically. Even the NanoVNAs with the later firmwares can compute these things automatically for you, right? But this is how it was done. I think it's always instructive to kind of understand what was actually going on, 60 years ago, 70 years ago, before we had these tools available to us. So a couple things I'll just point out here and kind of in closing. I do have a number of videos related to the NanoVNA up on my YouTube channel. This just indicates, a couple of those. Number 314 is the one that we played earlier, a couple of slides ago. But I've got a whole basics of what a VNA is in video 312. 313 talks about how and why to perform a calibration. And then other things like measuring coax length, or looking at the effect of adding coax length, or measuring the impedance of unknown coax, or even tuning a duplexer, some other topics using the NanoVNA that may be of interest to us as hams. And then finally, a little bit of summary here. Smith chart, again, is a pretty useful tool for determining SWR, return loss, and much more. And again, we've only scratched the surface of what you can do with a Smith chart. The transmission line impedance transformations are really kind of open your eyes up to what's going on when you add and remove transmission line between your load, whether an antenna and your transmitter. Could be used to really aid tuning an antenna or adjusting a tuner, and then matching network design, and literally dozens of things that we haven't touched on. So a little bit of a shameless plug. Like I said, all these videos you can find on my YouTube channel. It's just youtube.com/W2AEW. And of course, if you have any questions, you can always shoot me an email. That's my email address, just my call at awrl.net. But that's what I have. Guess we can open it up if anybody has any questions. I'm not sure if anything came up in the chat or not. But if any questions at all, please certainly let me know.
Certainly someone's got questions. There was a lot of things were presented here. All pretty cool. Lots of different uses. So anybody ask, someone's got it.
I'll
Oh,
go.
go ahead, Jim.
Okay. So Alan, in a practical world, I just want to make sure I'm processing it in my head, but by doing this advanced work to better match my antenna versus what a tuner or whatever might do, I'm increasing my antenna performance by through the feed line by getting the more out of it than I probably am today. Is that the takeaway?
Well, if you have a tuner and you've adjusted it to minimize the SWR, you're going to achieve that same result if you use the NanoVNA versus doing it the normal way of picking a frequency and going. The insight that you get with a NanoVNA is more similar to the insight you get when using a more advanced antenna analyzer, like a Rig Expert or something like that, where you can sweep it over frequency. And by being able to look at multiple versions of that impedance and matching, like return loss, the SWR, and the complex impedance on the Smith chart at the same time, it may give you a more intuitive feel to say, oh, by adjusting this, that's how I'm adjusting this curve. So you get a better feel for what's going on over a frequency range in terms of adjusting things. It's more about just giving you some insight. Now, if you were designing something like a matching network and you needed to know the actual complex impedance, a VNA is going to give you a more accurate result than something like an antenna analyzer will. Like an MFJ, 259 will tell you impedance and reactance, but it doesn't tell you the sign of the reactance. It doesn't tell you if it's inductive or capacitive, right? A VNA will. Okay.
We have some comments in chat, getting some good reviews in the.
Okay. Well, so hopefully, if nothing else, it gives you a little idea. If you look at a Smith chart, you know what it is now, right? Oh, I'm measuring impedance. That's inductive. That's reactive. That's a bad SWR. That's a good SWR. Just by looking at where things are in a Smith chart, now you should know that. So,
Anybody else? Someone spoke up earlier before Jim did.
Yeah, I was just going to say,
Hey,
I'm studying for my extra test right now. Everything that you covered is on that extra test, so
all right.
it's a big help. I
Great,
appreciate
excellent.
it. Good
Oh,
job.
Thank you.
I have to say that's the best explanation of Swiss charts I've ever heard.
Oh, thank you. Thank you.
I took the extra test with a woman who I don't know how to describe her, but let me just say she passed it with one. They said she had a question wrong, and she ended up spending 6 months with them trying to prove that she didn't have the question wrong.
Okay.
She finally convinced him. I guess she was right.
Oh, wow. Okay.
but she had some way, she was talking about Smith charts and remembering it for the extra test, and how she had something where you let's see if I get, where you push people away, and they were talking about versus pushing them right to left, and she was relating the axes on the Smith chart to I guess it was admittance and what was the
Admittance and impedance. Yeah.
yeah, but it was actually it was terms. Anyway, I'll think it actually matched for her, like if a woman pushes, or if somebody pushes forward, you're pushing someone away.
Okay.
And that actually, the term she used for that was actually related to the radio terms. And okay.
Yeah,
Yeah.
there's a lot of ways that you can kind of think about these things. I kind of, through the language that I typically use, but I'm an electrical engineer, an application engineer, so it's kind of what I've been trained to do. But there are a lot of ways to think about this. And again, you can just kind of think about it in ways that make sense to you. But at the end of the day, if you're looking at something on a Smith chart, the closer you are to center, the closer you are to matching the transmission line impedance. If you're above or below the equator, if you will, indicates that you've got either an inductive or capacitive component to that complex impedance.
So there are obviously there are formulas that you get what you did on the chart, where you just start off with a complex impedance.
Yeah.
And then you move up to one circle, and then you move back around because you're trying to get to the 0 point. I guess there are equations that you can compute that from the.
Yeah, there are mathematical ways of getting there, but it's a lot easier to do graphically. And
I see that. Yeah.
And even especially if you're trying to figure, okay, I'm going to add transmission line length. How much does that change my impedance? The computations to do that involve like these hyperbolic tangent functions. It's just right versus drawing a little arc. Which of those is easier?
I got
I have to ask you, was that a guitar pick I saw in your video?
It was actually. That's the stylus I use for that NanoVNA is actually a guitar pick. So yeah.
Okay, that's a cool idea. Those things are very tiny.
Yeah, because some of I've actually got 3 NanoVNAs, and one of them didn't come with anything. One came with like one of those little Nintendo DS styluses, which works. But that one actually came with the guitar pick with a hole drilled in it with a little lanyard. So it's actually what came with it. So somebody else had the brilliant idea. It wasn't me.
You get one of those banjo picks with around your finger.
There you go. That would work too.
Bob, you got any questions? Bob Bennett, I remembered you talking about calibration of NanoVNAs when we talked about the NanoVNAs. Do you have any follow-up NanoVNA questions from here?
No, but I'm gonna go back and watch the video over and over and over again.
Okay.
Yeah. Great.
I saw Bob Bennett here, and I've got a Bob Bennett that lives not too far from me here, is also a ham, but you're not the same Bob Bennett.
Yeah, well, I was a ways north of you up in Bloomingdale,
Okay.
but I used to come to the.
Are there tools, you're doing this all on the graph paper, et cetera. Is there something on the computer or computer programs that are more mechanized for doing this?
There are. There's one called SimSmith, SIM Smith. That's probably the best Smith chart tool that's out there that runs on Windows PC. I think actually there's compilers for Linux as well if you're a Linux guy. But SimSmith, not the easiest tool to use, but certainly the most comprehensive to use. And there's another guy on YouTube. If you go to the SimSmith site, it'll point you to this other guy, Larry Bento's YouTube page, where he's got many, many, many tutorials on how to use SimSmith. But it does what I did, graphically, if you will. It can do it all on the computer and plot things out for you and show you the effects of adding these various networks and stuff like that. So SimSmith is probably the best one. There are other ones that are out there as well, but SimSmith, I think, is the best one that's out there.
Anyone else? Bob? Your presentation, is your presentation available? Is it on the web or
I'll email you a PDF of it.
Oh, thanks.
Share it with whoever you'd like.
Yeah, because at least I'd want to get the your video, that slide with the video links on there.
Yeah. So the
But I want
links
the
aren't
rest of
there,
it.
but they tell you the numbers, of course. Because I don't think I got the hyperlinks in the PowerPoint, but you can just search my YouTube channel for that number and find them. But then again, you can share the PDF. The PDF won't have all the animations and it won't have the live video in it, but at least you can use it as a reference to move forward and to use along with your recording of today's meeting.
Welcome back, everybody. Sam Ford, I'm to the students here.
I think it's someone in the background.
Yeah, there you
Yeah,
go.
yeah. So we've got a YouTube channel, Atlanta Radio Club YouTube channel, and this recording will be on there
Okay, very good.
in 2 or 3 days, and I'll send you the link
Great, thank you.
if you want to check it out.
Yeah, because I did the same presentation several months ago for, I think it was the San Fernando Valley Radio Club in California, W6SD, I think it is. Yeah, SD, maybe it was San Diego, but they've actually got it on their YouTube channel as well. So, but that's fine. Absolutely.
That's great. Yeah, I know. I'm gonna look up Smith charts, now, and I have a point. I know where to go from. It's not something where it's totally unknown. I
Right.
can go probably to Wikipedia on Smith chart and understand that a lot better than before your
Yeah.
talk.
Yeah, sometimes just getting that high level view is like, oh, well, that's what that means. It makes a lot more sense to follow it from there. So.
Are the Smith chart pads? I guess are there different Smith chart?
So the Smith chart itself is still actually licensed to one company, but you just do a search with Google for a Smith chart PDF, you'll find dozens and dozens of them. Some of them, so you could download them, print them yourself just as a PDF file. And there's a couple of decent ones out there that are the combination Smith charts that have the admittance and the impedance curves on them. Some others only have, the red set of curves, if you will. But just do a search for Smith chart PDF and you'll find dozens of them.
Which ones were you using?
If you do a search for Smith chart and for PDFs, it's probably the third or fourth link. Just open up each one and you'll just I don't remember where I got it. I just found it and downloaded it, and I've had it for years. So
Because I want to find the one with the scale on the bottom.
Yeah. So yeah, you can just open up each PDF file and see that it's got the scale and both sets of curves on it, and then you're good to go.
That sounds great.
Alan, this is Warren, KD4Z.
Yeah.
Great presentation. Love your videos.
Thank you.
There have been quite a few versions of the NanoVNA over the years. I've got one of the early ones, and I've got one of the larger screen ones. Is there really anything significantly changed worth buying in again on the current offerings?
That's a good question. It depends on how much of an obsession you have with the test equipment like me. But the reality is the initial versions were a relatively small screen, as you know, 2.8-inch screen, and went up to about 1.5 gigahertz, and we're fairly limited in dynamic range. The later version, then there was a 4-inch version of that called the NanoVNA H4, had a 4-inch screen. I've got one of those. I use that a lot. Again, it's probably one of the earlier bits of hardware, but it works really well. It's very lightweight, and then it's only like $60 or $70, so you wouldn't feel too terrible if it broke, right? The later versions were called V2s. The V2s generally went up to a little bit higher frequency range, I think up to 3 gig, and had a little better dynamic range. So that was important if you're looking at things like filters. You want to look at the stop band characteristics of a filter, make sure it's a good 60 or 70 dB down, or you're trying to measure something like maybe a repeater duplexer or something like that. You want the deepest dynamic range you can get. Most of the NanoVNAs aren't going to have really good enough dynamic range to do a great job on a duplexer, but the V2s will do better than the originals will. So I've got one of the V2s with N connectors on it, and that was called the SAA V-2N or something like that. I've got one of those. And the next one that kind of tempted me to put some money down was kind of the improved version of the V2. It's kind of the V2 Plus, and it was called the V2 Plus 4. that had a 4-inch display, goes up to, I think, 3 gigahertz, maybe even more, maybe 4. I don't remember now. SMA connectors, nice metal case instead of a plastic case. Firmware brings you up to like 400 something points or something like that, and about twice as fast in terms of sweep as the others. Now, that was about a year and a half ago. In the year and a half since then, there have been more developments that I've kind of lost touch with a little bit. There's a version 3 coming out. There's the same group of guys are developing a 6 gigahertz version, but now even the 6 gigahertz version is getting up to be several $100s, right? So it really kind of depends on what your price point is. If you want to spend less than $100, you're kind of in the original versions. The V2s are typically between 1 and 200. You get up to the higher speed, higher resolution ones, you're typically over $300. So it really comes down to that, more than anything else. And the good domestic source that I've found for these things, because most of these things are made in China, is R&L Electronics. They've usually got a pretty good selection of, what's kind of out there and available.
Thank you. That's where I've got the H4 from. They're the only ones that seem to have them in stock. So,
Yep.
And definitely more reputable than fly-by-night eBay. So
Exactly right.
Yeah.
Exactly.
A follow-up question about that. Are they're made by various companies in China, or just, it's not just one company making them? That's
the whole problem with the NanoVNA, is that the NanoVNA started off life as a kind of an open source project. And somebody kind of took it upon themselves, built this thing, they published schematics, they published the software, and then China Incorporated started mass producing these things, and they didn't know where they came from and who built them, and nobody got credit. The original developers didn't get credit for it and all that kind of stuff. And that's the case of the NanoVNA H and the H4. There's just lots of people that are making them out there. There are a couple of manufacturers that the original designers kind of endorse, and then there's just a bunch of clones. And that's why I went to R&L, because R&L kind of made sure they were buying units from kind of the reputable manufacturers. Okay. The later versions, like the V2s, the design was not made public domain. All right, so there are just a limited number of people making the V2s, and you generally have to source those from those manufacturers in China through like Alibaba or whatever it is. But there's a link on the NanoVNA V2 website of the official places to buy them from, and I bought it through one of those China locations, and I had it in my hands in a week and a half. So.
There are, I'm sure, different websites. Are there any more official?
Yeah, so if I actually have a presentation that I do on the NanoVNAs, and I've got the websites for them, because so there's NanoVNA.com is kind of the open source, everything, basic open source NanoVNA stuff. The V2s and the upcoming V3s, it's RFE.org or nanorfe.com. I have to do some searching on that, but that is kind of the website, network, if you will, of the original developers for the V2s. And then in there, you'll find pages where they've got the recommended, vendors and things like that. So, but it's nanorfe.com, I think.
Okay, and then Nano V2. Okay, that's great. Anyone else? Last call for questions. You got to have something. I always say, if no one has questions, they must have understood everything 100%.
Or I put everybody to sleep, one or the other.
It always makes me feel bad, because people say, yeah, I got it all. How come you have a question? All right, I guess that's it then. We're going to let you get back to
all right. Very good.
New Jersey.
Well, thanks again for having me, and again, I'm glad you guys found this useful.
Alan, thank you for agreeing at the last minute to do it. Appreciate it. And you'll probably be we'll certainly be checking out your videos.
All right, sounds great.
Thank you, Alan.
Thanks a lot.
Good night, guys. Take care.
Thank you.
Thank you.
All right, thank you.
Okay, so the election's done, and we got the repeater report. That's about it. We have lunch tomorrow at Mellow Mushroom at 12:30. You know, we are doing the lunch every week, and we've got some operating events coming up. I don't know what they are. We'll see what the new board says, and there should be some announcements, I'm sure, pretty soon about what the plans are going to be to get out in a park or get out somewhere and just get on the radio.
Hey, Rob.
Yes.
Yeah, let me take it for a minute.
Go ahead. Go ahead. Go ahead, John. It's all yours.
Yeah. Thanks for everybody for being here tonight, and thanks for once again entrusting the leadership of the club to myself and Rob, Aid, Ed, and Bill. We will be posting some upcoming events here shortly. We got some POTA events and some other things coming up, so stay tuned. If you're not subscribing, please do subscribe to our .io group and Facebook page. If you're obviously financially, it helps to support the club. And if you're a past supporter and not sure if you've renewed yet or not, or up to date, you can reach out to Aid, our club secretary and treasurer, through email if you'd like, secretary@atlantaradioclub.org, and or treasurer or any one of the boards, and we can let you know whether or not you're up to date or not on dues. And of course, more than your financial support, but your actual physical support by participating in club activities and volunteering to do things is a great help also. We're still looking for someone to run with the newsletter, to put it together, put it together, and get it emailed to everybody. So if you have an interest in doing that, please do contact me, president@atlantaradioclub.org. Thanks to Skip, our outgoing vice president, injected a lot of energy into the club this year with his enthusiasm for things. So thanks to Skip for his work this past year, and looking forward to having Ed on the board this year. And as always, like I said, this club runs when all of us participate and take a little bit and do a little part to make it work. So please do, as we call for help on things, please do reach out to us and say, yes, I would like to help. And there'll be opportunities coming up soon on that kind of stuff. So just keep your ear out for calls for help. Thanks to Jeff and Steven this past year and going forward, keeping our repeaters in shape, or at least working on getting them in shape. If you have an interest in helping them on that, please let us know, and we'll certainly get you on that committee too. So like I said, if you have an interest in doing something and don't know what you could do, reach out. We'll find something for you. And that's about all I have for right now. I don't know. I just got back on, so I don't know if Aid had any reports, if he's even on here tonight, from the treasurer or secretary standpoint, membership standpoint. Aid?
Yes. I'll give a brief treasurer report. We have a total of $14,249.72 in the bank, and $113.84 PayPal. So we are solvent. And I don't have the membership number. Let me see if I can pull that up.
Okay, I lost you there a little bit. I don't know if I'm assuming you were done. You kind of faded out on me, but were you done, Aid? I couldn't hear you.
Can you hear me now?
Yes, go ahead.
Okay. Did you hear a PayPal number?
Yeah, it seemed to kind of fade out there at the end. I don't have you on video, so I'm in the car and it won't let me swap back to video right now. So I can't see anything. I can only hear. So
membership wise, we have 83 active members.
Okay, good deal. We could always use more. So, like I said, if you're not sure whether or not you're financially in the black, contact Aid and he can let you know for sure, or any one of the other board members. Does anybody have any questions, comments, suggestions for the board for the upcoming year? We'd be more than happy to take them if you're willing to give them now, or at a later date's fine too. You can hit us with an email. Any comments or suggestions or questions from the board at this time?
I'll just say at lunch tomorrow, I'm going to bring a Smith chart. That's my comment.
Okay.
Good sauce.
Yeah, if you if you get a chance, come join us for lunch on Fridays. We've got a pretty solid group going, so we've always got room for more at the table. So please do join us on Fridays at the Mellow Mushroom
In
and
Brookhaven.
in Brookhaven, right there across from the Brookhaven MARTA station. So easy to find. It's sort of, I guess, it's kind of behind the Dunkin' Donuts, I guess, off the main drag, but right across from the bank. So please do join us. I don't have any more at the moment. Anything else from anybody else? All right, nothing heard. Well, like I said, we're always looking for feedback from club members. So if you got any comments or suggestions, things you'd like to see, programs, Rob's always looking for suggestions for Thursday programs.
Yep.
I don't know yet when we're going to be back to in person. We're kind of working on that at the moment. So there's always a chance next month, but at the moment it might be back Zoom again next month. So just stay tuned. Also, I forgot, thanks to Jim, Newt, Lane, even Val, Bruce, all those guys for agreeing to have some part in the elections committee. That's always an important thing. So thank you to them too for their short work this election cycle. So thanks to them. Anything else, guys? If not, I guess we'll call it a night. It's about 9 o'clock. Great program again. And if nothing else, join us Sunday night for the Sunday Night Net at 8 o'clock or lunch tomorrow at the Mellow Mushroom in Brookhaven. And if not, we'll call it a night. And everybody have a good, safe holiday this weekend. Shelby Hamfest is this weekend in Shelby, North Carolina. It's about, 4 hours up the interstate. So if you've never been, give that one a shout and take a look. It's a fun one to go to. So anything else, Rob?
No, I'm good.
All right. Well, everybody, like I said, have a safe weekend and enjoy your holiday. And we'll see you at the next opportunity, whether it's lunch or net or one of our activities coming up. So everybody have a good evening.
Thanks, John. Thanks, Rob.
Take care. Have a great weekend, everyone.
73.